Let's do another example. A sample of a compound is decomposed in the laboratory and produces 165 grams of carbon, 27.8 grams of hydrogen, and 220.2 grams of oxygen. Calculate the empirical formula of the compound. So this is going to follow the same steps. First, we have to start with the masses. Here they're provided for us. So we've got 165 grams of carbon. We want to convert that to moles because a chemical formula relates numbers of atoms. And so moles are a counting number, and that's going to be helpful. So we're multiplying by moles, dividing by grams. That conversion factor is the molar mass, which we get off the periodic table. 1 mole of carbon is 12.01 grams. So the units work out. So we got 165 grams divided by 12.01. So this is 13.7. If we're counting sig figs, this would be 3 sig figs. And so we want to be sure we keep at least 2 more after that. Because we don't want to round off. We want to keep extras if possible. So there's my moles of carbon. And then I'm going to look at the next element, which is hydrogen. 27.8 grams of hydrogen. And I'm going to convert that to moles in the same way. Multiply by moles, divide by grams. For hydrogen, 1 mole weighs 1.008 grams. Grams cancel out. 27.8 divided by 1.008. Again, 3 sig figs and carry 2 extras. 27.579 moles of hydrogen. The last element is oxygen. 220.2 grams of oxygen. Converting that to moles. Moles per gram. 1 mole of oxygen weighs 16 grams. 220.2 divided by 16, 13.762 moles of oxygen. Any questions yet? Yeah.
For the molar mass of oxygen, do we use 15.999 or 16.8?
You can use what's on your periodic table, the whole thing, or you can round to 4 sig figs, never round more. I use 4 sig figs because I've got most of them memorized, and it just makes the lecture go faster. Yeah.
Never mind.
Okay. So we start with masses of each of the elements. We convert to moles. Now these are not nice numbers that would give us a beautiful chemical formula. You know, C13.738. That's not a whole number, and we can't just round these off. What we need is a ratio of whole numbers. And to do that, we're going to look at all of these numbers we got, pick the smallest one. If this is the smallest one. We're going to divide all of them by the smallest number. So when I divide the smallest by itself, of course, I get 1. So one of the elements will always come out to be exactly 1. This other one I'm going to divide by 13.738. So 27.579 divided by 13.738. This gives me 2.0074. That's pretty close to a whole number. And then taking this one, you can kind of predict that's going to be close to 1. But you really need to do the math. Don't just guess. So divide by 13.738. And that comes out to be 1.0017. So when we look at these are ratios now. So the mole units cancel out because we're dividing by moles. So the moles cancel out. I was a little sloppy there. when we look at these numbers, it's easiest if they're whole numbers, but we can't just do wishful rounding. This number, if it's more than 0.2 away from a whole number, you can't round it. In this case, this is close enough to round, and that's close enough to round. So this is going to be 2, this is going to be 1. Those are the subscripts for these elements in the chemical formula. So for carbon, the subscript is 1, which we don't write. For hydrogen, the subscript is 2. And for oxygen, the subscript is 1. And that's the empirical formula.
Is it okay to use the less specific mass in order to get a more likely whole number, like 16.0 instead of 15.9?
No, you should never round molar masses for the specific purpose of getting rounder numbers at the end.
That's what I said in the tutorials.
Honestly, yeah, don't. That's not good advice. Yes?
And on the online homework, we needed to say this, but I wasn't sure of what. I'm not sure if it was this one that you had mentioned not to use them, but then they're asking.
Well, it depends. In terms of significant figures, it depends on what type of problem you're doing. So in this problem, because we're getting to an empirical formula has to have whole numbers. So we don't necessarily need to be super careful with significant figures. What you need to do is use more than enough. Okay? Because sometimes students will take this and 13.7, they'll round that to 14. And they'll round this to 28. And they'll round this to 14. And sometimes it'll work out okay, but many times it'll get you the wrong formula. So don't round these numbers. And so we don't have to follow sig figs to end up with the correct number of sig figs in our formula, because they're going to be whole numbers. But you want to make sure that you use I highly recommend 2 more than sig fig rules require. If you want to write all the digits, that is absolutely fine here. It's a little tedious, but it will not cause you error. If you round too much, it will cause error. Any other questions? Yeah.
Would this be an example of not getting whole numbers? Because I know on a previous slide you talked about fractional subscript.
This is not an example of not getting whole numbers. I believe the next example is one that doesn't give us whole numbers. So in this example, ibuprofen and aspirin substitute has the mass percent composition given here. So calculate the empirical formula of ibuprofen. We're not given masses, we're given a percent, a mass percent composition. So what do? Well, you can make it into a decimal. What's easiest is to say, well, if I had a 100-gram sample, how many grams of carbon would I have? 75.69 grams. Okay? The percent composition is valid for any amount. That's the beauty of a percent, right? It's always true. So we can choose an amount that makes things easier for us. If we choose 100 grams, then the percentage, all we have to do is change the percent sign to gram. So that's what we do. So then for carbon, we have 75.69 grams of carbon. And we're going to convert that. And do this a little quicker. Or try to anyway. My starting number has 4 significant figures here. I used a rounded molar mass, but 4 sig figs still. You definitely don't want to round to 2 or 3. Never go less than 4 sig figs in your molar masses. So then I want to make sure at the very minimum, then I have 4 sig figs here, and it's much better to put 2 extras out there. That's moles of carbon. The percentage of hydrogen is 8.8%, so that means in a 100-gram sample, I would have 8.80 grams of hydrogen. So 8.8 divided by 1.00. 8.73. 0.15. Yes?
I'm sorry, why do you convert it to masses instead of going with the percents?
Well, how am I going to convert a percent to moles?
The amount within the compound.
I don't have a conversion factor between a percentage and the number of moles.
Well, you mentioned 75.69 out of a 100-gram sample, or 100% of the sample. Or...
Yeah, so
Are you saying because it's that percentage, 75.69, if it was a 100-gram sample, then you could...
then this would be the mass of carbon. What I'm saying is we're going to choose a 100-gram sample. So choose 100 grams. Because then we don't actually have to do the math with the percentage. We can just change percent to gram.
So would it also be a possibility of adding the molar masses of carbon, hydrogen, oxygen, and then multiplying it by converted percentage?
No, you can't just add the molar masses and multiply by the percentages. I'm not following that. We could talk about that later. This really is the fastest way to do it. For oxygen, we got 15.51 grams. 1 mole of oxygen to 16.00 grams of oxygen. .969375 of oxygen. Yes?
And last thing, why don't you write 100 grams in the denominator?
Okay, so what I'm doing is I'm saying I have a 100-gram sample. So I have 100 grams of ibuprofen times 75.69 grams of carbon per 100 grams of ibuprofen. And then when I do the math, I get 75.69 grams of carbon. So I am doing that. I'm just not writing it down, because it's not necessary. Okay, so this is what we're doing in our heads. This is why I say just choose a 100-gram sample. So if you understand that, that's awesome. If you don't, I'm telling you a hack. Replace percent with gram, and that'll work. Bless you. So what's the next step after getting moles of each element? Divide by the smallest number of moles. Now, all these examples we're doing here in lecture, these moles come out to be pretty large numbers. Okay, we're doing an experiment today, and your moles will probably come out to be 0.000 something, because you have a very small sample size. So don't be alarmed by that. But this is the smallest one. So I'm dividing by the smallest, and this one ends up being 1. And I'm going to take this one and divide by the smallest, 0.969375. And this one comes out to be 9.00596. And the carbon oops, 969. This one comes out to be 6.50135. So we always end up with one of them being exactly 1. This is 9.005. We could round that to 9, but what are we going to do with 6.5? We can't round that to 7. This is 0.5 away from a whole number. It needs to be close to a whole number. When you do this on problems, on an exam, on a homework, on a worksheet, the numbers that can be rounded are going to come out pretty darn close. When you do this in lab, it's going to be a bit iffier. We need to make this into a whole number. If we recognize fractional equivalence of decimal equivalence of fractions, 0.5 is 1/2, right? This is 6.5 or 13 halves, and 13 halves. And so if we multiply by 2, we're going to get a whole number. If you don't recognize those equivalents, just try multiplying by 2 and see what happens. If you don't get a pretty close to a whole number, try multiplying that number by 3. Try 4, try 5, okay? So I'm going to take the 6.50135 and multiply by 2. So I multiply this by 2, and I get 13.0027. Oh, there, that's nice. That's 13. If I multiply 1, I have to multiply all of them, otherwise I mess up the ratio. So I have to multiply this one by 2 also. So that gives me 18.0119. Still close enough to round. So that's going to be 18. And 1 times 2, is 2.
So,
Yes?
we only use this multiplication thing only if like one number is half
Yeah.
and a half.
You only multiply all of these if they can't be rounded to whole numbers. So what we're getting here is a ratio of 13 to 18 to 2. That's the smallest whole number ratio. You can't simplify that because 13 is a prime number. The ratio of 6.5 to 9 to 1 is the same ratio, but it's not whole numbers. Has to be whole numbers because in a molecule you can't have 6.5 carbon atoms, right? So our formula then is going to be C13H18O2. Any questions?
Is there a way to test that and make sure that your answer is correct?
Well, you can test the ratio. I mean, if you divide 13 by 18, you'll get the same number as if you divide 6.50135 by 9.00596, or very, very close. Here's another one. Instead of percent composition, here we're given reaction data. So this is like the data we'll have in lab today. A sample, 1.56 gram sample of copper reacts with oxygen to form 1.95 grams of the metal oxide. What is the formula of the metal oxide? To find the formula, we need the masses of each element. What are the 2 elements that are present? Copper and oxygen, right? So we've got copper, and we've got oxygen. Well, they gave us the mass of copper, 1.56 grams of copper. Well, let's convert that to moles. 1 mole of copper, 63.5. Did I do that right? Yeah. So 1.56 divided by 63.55 gives me 0.0245 47 moles of copper. What's the mass of oxygen? Is it given in the problem? No, because it's hard to weigh oxygen. It's a gas, right? This is the mass of the product, the metal oxide. Why does that weigh more than the original sample of copper? Because it reacted with oxygen. So the difference in this mass and the mass of the oxide is the mass of oxygen. So we subtract. Oh, I'll stick that down here at the bottom. So 1.95 grams, that's copper plus oxygen. If we subtract 1.56 grams, just the copper, then we end up with the mass of the oxygen. So 1.95 minus 1.56, 0.39 grams, and that's the mass of the oxygen. Okay? So 0.39 grams of oxygen. We're going to convert that, moles and grams down here, 1 mole to 16. 0.39 divided by 16. 0.024375. That's not a 7. Moles of oxygen. Okay? Pick the smallest, divide both of them by the smallest. Well, the moles of oxygen is a little bit smaller. So that's going to be 1. And this ratio, one comes out to be 1.00708. This is close enough to the whole number 1 that we can round it. And so we've got a ratio of 1 mole of copper to 1 mole of oxygen. Any questions?
Copper to oxide.
It would be copper 2 oxide, yep.